So if we review our test on number 1A, it says evaluate the exponential function and we're given 4 to the x minus 4. We're making a table of values and we need to use at least 5 values. So you can then use any values you want to use. So what values do you want to use? Okay, perfect. 1, 2, 3, 4, 5. Those would probably be the ones that I recommend using on your test tomorrow, which is 1, 2, 3, 4, 5. Because they're the easiest ones to use. You can use whatever, but that's easiest. Okay, so if I plug in 1 and I get 4 to the first minus 4. 4 to the first is just 4. 4 minus 4 is 0. Okay. I do the same thing for 4 to the second minus 4. 4 squared is 16. 16 minus 4 is 12. Okay, so then if I keep going, 4 to the third minus 4. 4 to the third is 64. 64 minus 4 is 60. Alright, and then if you do the same thing for 4 and for 5, you should get 252 and 1020. If we look at 1B, we're going to do the same thing. We're going to make a table of values. So 1, 2, 3, 4, 5. So if I plug in 1, I get 7e to the first. So then if you plug that into your calculator, what do you get? Okay, so 19.028, rounded to 3 decimal places. If I plug in 2, then I get 7e squared, which is 1.723. If I plug in 3e, 7e cubed is 140.599. 7e to the fourth is 384.187. Oh, 382.187. And lastly, 7e to the fifth gives me 1038.892. So those should have been the values you should have got for 1 and 2, or I guess 1A and 1B. So if you just plug those into your calculators. If we do the same thing for 2A and B, we're going to be plugging these into our calculators and making a table of values. So I'm going to use 1, 2, 3, 4, and 5 again. So if I plug in 1, then I get 9 log base 5 of 1. Anyone know what that gives me? 0. Yep, should give me 0. Question. I plug in 2 and I get 9 log base 5 of 2. What do I even get for that one? Okay, so 3.876. If I plug in 3, I get 9 log base 5 of 3. Five. Okay, I was like, that seems really outrageous. Oh, okay. 6.144. Okay, that's what I had on here. I was like, well, maybe I did it wrong. All right, 9 log base 5 of 4. Perfect, 7.752, and 9 log base 5 of 5. 9, yep, because those just cancel, so we're just left with 9. Okay, so you should have got on the first one. If we look at the second one where we're doing natural log, somebody want to come up here and do that while I answer the board for the door? No? Cousin, go do that. Here. Oh, you're good. I didn't realize you paused it. Sorry. Okay. Okay, so if we graph the function for each of the x minus 1, we're just going to make a table of values. Or you can graph it on your graphing calculator and then sketch it, but write down some values either way. Okay, so I'm going to use like 0, 1, and 2. Small values are better because the bigger the exponent, then the bigger number you get. Okay, so if I plug in 3 to the 0 minus 1, 3 to the 0 is 1, 1 minus 1 is 0, okay, so now I've got a point at 0, 0. If I plug in 1, 3 to the first minus 1, 3 to the first is 3, minus 1 is 2, so over 1 up 2. And then if I plug in 2, 3 squared minus 1 is 8. So I know that my graph is going to look something like this, where it starts out flat and then gets steep. Oh, not what I wanted. Next. Okay. Alright, so if I look at part B, log base 3 of x plus 1. This one is just going to be easier to put into your calculator. Just FYI. Just put it in your y equals and then graph it, but then copy down some values from your table. So now I'm going to have values of 0, 0, 1, 0.631. You could actually put these in your calculator if you wanted to, but it's just easier just to graph it. So 0, 0, 1, 0, 6.3, and over 2 up 1. So I know that my graph is going to look something like that. Is that sort of what everybody got? Okay. All right. If I look at number 4, it says change the base of the log to evaluate. So we've got log base 2 of 128. And our formula for change of base is log of x divided by log of a, where a is your base. So I know that a is going to equal 2, and 128 is your x. So I know that 128 is going to be my x. So then if I plug that in, then I'm going to get log of 128 divided by log of 2. And so what does that give me? 7. Perfect. Yep. Okay, if I look at the second one, I'm going to do the same thing. Log of x divided by log of a. 1 over 125 is my x, and 5 is my a. So then if I plug that in, then I get log of 1 over 125 divided by log of 5. So what do we get for that one? -3. Perfect. Alright, so far that was all just stuff basically that we did on our calculators. Now we're going to get into some actual manipulating some logs. Okay. So if I look at number 5, we're expanding the expression natural log of the square root of 2x to the 5th times x plus 5. Okay, so the first thing I want to do is I'm going to change this square root into an exponent of 1/2. So I'm going to have natural log of 2x to the 5th times x plus 5. All to the 1/2 power, because square root's the same thing as an exponent of 1/2. And I do that because then I can roll this 1/2 down to the front. So I'm going to get 1/2 natural log of 2x to the 5th times x plus 5. Okay, so then I'm going to start breaking that up. So I know that I'm going to have 1/2 natural log of 2x to the 5th plus, because multiplication changes to addition, 1/2 natural log of x plus 5. And then I can go further into breaking this up by going 1/2 natural log of 2 plus 1/2 natural log of x to the 5th plus 1/2 natural log of x plus 5, where I broke up the 2x to the 5th into 2 and x to the 5th. And then my last step is going to be to roll this exponent down to the front. And so I'm going to get 1/2 natural log of 2 plus 5 times 1/2 is 5/2, or 2.5 natural log of x plus 1/2 natural log of x plus 5. So then what's in blue would be my final answer. Okay, so any questions on that one? Okay, if I look at 5b, I have log of 6x over 3y squared. I know that division leads to subtraction when I break things up. So I know that I'm going to get log of 6x minus log of 3y squared. Okay, which then is the same thing as log of 6 plus log of x if I break up the 6x. Minus, if I break up the 3y squared, I get log of 3 plus log of y squared. And I'm going to roll down my 2 and distribute my negative. So then I'm going to get log of 6 plus log of x minus log of 3 minus 2 log y. And so what's in green then would be my final answer. Okay. On 6a, we're doing the opposite, so we're condensing the expression. So I'm given 9 times natural log of k minus natural log of k plus 5 plus 2 natural log of k minus 5. And I'm going to condense that. So the first thing I would get is that I can roll this 9 back up to be an exponent, and I can change this subtraction to division. So I know that I'm going to get natural log of k divided by natural log of k plus 5, all to the 9th power. And I'm going to do the same thing here, is just roll this 2 up. So plus natural log of k minus 5 to the 2nd power. Okay, so I'm going to pull these natural logs out front. So I know I'm going to have natural log of k to the 9th divided by k plus 5 to the 9th. I distributed that 9 to both of them. And then I still have plus natural log of k minus 5 squared. And then the last thing that I know is that addition changes to multiplication. So I know that this is really like natural log of k to the 9th over k plus 5 to the 9th, all times k minus 5 squared. So what's in red would be your final answer once you condensed it. If I look at 6b, I have negative 8 log base 6 of 2x minus 1/3 log base 6 of 7x plus 2. Okay, so the first thing I'm going to do is I'm going to roll my exponents up. So I'm going to roll this 1/8 up, I'm going to roll this 1/3 up, and so I'm going to end up with log base 6 of 2x to the negative 8 power minus log base 6 of 7x plus 2 to the 1/3 power. Okay, so then I know that this negative exponent actually becomes a fraction of 2x to the 8th power. And to make it positive, I have to move it to the bottom, so I know I'm going to get log base 6 of 1 over 2x to the 8th power, and I know that this 1/3 becomes a cube root, so minus log base 6 of the cube root of 7x plus 2. And then the last thing I know is that this changes to division, so I'm going to end up with log base 6 of 1 over 2x to the 8th power times the cube root of 7x plus 2.
That's the answer.
That's the answer. All right, so any questions on condensing? Okay. All right, if I look at number 7, I have 2 to the 2x minus 3 equals 32, and I'm going to solve that. So I'm going to try to get my bases to be the same. So I'm going to leave the 2 to the 2x minus 3 to be the same. And I know that 32 is the same thing as 2 to what power? 5th. Okay. So then when my bases are the same, I can set my exponents equal to each other. So 2x minus 3 is equal to 5. So if I add 3, 5 plus 3 is 5 plus 3 is 8, divided by 2, divided by 2, so x equals 4. Alright, if I look at b, I have 10 minus 6 natural log of x equals 10. So I'm going to subtract 10 from both sides. So I get negative 6 natural log of x equals 0. And if I divide by negative 6, then I get natural log of x equals 0. And then to get rid of a natural log, I know that I need to make this have a base of e, so e to the natural log of x equals e to the 0. And then those cancel, and e to the 0 is just 1, because anything to the 0 exponent is 1. Alright, number 8. says determine the time necessary for $2,000 to double at an interest rate of 10% when it's compounded annually and continuously. Okay, so that first formula up there is our annually formula, and the second one is our continuously formula. Know that if $2,000 doubles, that it's going to give me $4,000. So the amount that I'm looking for is $4,000. I'm starting with $2,000. My interest rate is 0.1% over the number of times it's compounded annually. It's compounded once per year. And I'm looking for my time. Okay, so if I go to simplify that, 1 plus 0.1 divided by 1 is just 1.1 to the t. Okay, so then I divide by 2,000. $4,000 divided by 2,000 is 2. So 2 equals 1.1 to the t power. And then how did we determine that we were going to get rid of a base of 1.1? We have to take the log of that base. So log of 1.1 of 1.1 to the t in order to get those to cancel. So we'll do the same thing on this side, log of 1.1 to the 2. Whenever you're trying to get rid of a base, you just take a log of that. So my log and base cancel. I get t equals, what is log base 1.1 of 2 actually equal to? 7.273. Okay, so 7.273. So it's going to take a little over 7 years for it to double when it's compounded annually. If we look at continuously, then our amount is also going to be 4,000. Our principal was 2,000. My rate was 0.1. And time is what I'm looking for. Okay, this one's easier. There's less steps. So first I'm going to divide by 2,000. So I get e to the 0.1 t equals 2. How do I get rid of a base of e? Take the natural log. Well, that's an ln, and then so natural log of e to the 0.1 t and natural log of 2. And these cancel, so I get 0.1 t equals natural log of 2. I divide by 0.1. So t equals natural log of 2 divided by 0.1. What is that? 6.931. Okay, so it would take a little under 7 years, almost 7 years, when it's compounded continuously for the amount to double. All right, and then the last one that we need to look at is our half-life formula for radioactive radium. Okay, so your half-life formula is always y equals your amount that you start with times 1/2 to the t, the time you're given, divided by your half-life years. Okay. So it says radioactive radium has a half-life of 1,599 years. So I know that my half-life is 1,599. Okay. It says if you start with 20 grams, so the amount I start with is 20, how much radioactive radium is left after 1,000 years? So the time that I'm going to test for is 1,000 years. So if I plug that all in, then I get y equals 20 times 1/2 to the 1,000 divided by 1,599. Okay, well, what's 1,000 divided by 1,599? Perfect, 0.625. So I get 20 times 1/2 to the 0.625 power. So then put 1/2 to the 0.625 power in your calculator, take that times 20, and then let's see what you get. $12.968. Okay, so 12.968. So we would have 12.968 grams left over afterwards.